As you know, this is part 2 of what we talked about a couple of weeks ago, where I went over some of the physics that led up to the possibility of a bomb. And the basic idea was that there are nuclear phenomena that will pull the protons and neutrons more tightly together. And in doing that, they release energy. And oddly enough, one of these is to break a heavy nucleus into 2 parts, because it turns out the 2 parts bind their neutrons and protons more tightly, and as a result, they release energy. And they release a lot of energy. And that, of course, was the temptation, the lure of nuclear power and the nuclear bomb. Now, actually, people knew about this energy since about 1900. What they didn't know was how to get it out. And it depended on the discovery in 1939 of nuclear fission, that when you could break a large nucleus of uranium into 2 pieces, and that as a result, you would get out a couple of hundred of MeV of energy. Now, you remember I tried to give you a scaling of this kind of energy by giving you an example of the Hindenburg burning, as it burned 200,000 cubic meters, some couple of multi-tons of hydrogen gas. And that's, the unit of energy there was 5 electron volts, 5 electron volts. Whereas the unit of energy coming out of a fission is 200 million electron volts. That's a lot bigger. And right away, people knew that there was perhaps a possible source of power and a source of a bomb. What they didn't know quite was how to get it. There were several things that had to happen before you could have a bomb. And between the discovery of fission in really just January 1939 and the decision to go forward with the Manhattan Project, there were several things you had to establish. And I'm going to just recap a little bit before I go through the Manhattan Project. I want you to understand what some of those things were. So the first slide that you see here is a kind of schematic model of a bomb, of a atomic nucleus. Immensely dense, very compact, at the very tiny diameter, kind of 10 to the minus 12, 10 to the minus 15 meters. You don't know what that means. 10 to the minus 15 is just minute, 15 zeros with a 1 a decimal point and a 15 zeros. That's pretty small.
Excuse me, Charlie?
Yes.
Could you use slideshow mode to make the slide bigger?
I thought I was.
No, we're seeing the upcoming things like the...
Well, let me see what's the matter here. Oh, I see. Something is wrong. I'm not getting displayed on my screen what you have on your screen.
So we are seeing the presenter view.
Yeah. I want to be showing the browser view, because otherwise I have something on both my screens, and I only want something on one screen.
On the lower left, it says normal view, and to the left of that is something that looks... There's 3 buttons on the very lower left of your screen.
No, there aren't.
Can you try the 3rd one in, maybe?
Let me get out of full screen mode here to see what's going on.
He's on an Apple device. I don't know where the buttons are on that one.
I have a PC and I don't see any slides. I just see Charlie.
When I've done this,
you're getting the worst half of the deal then. Let's see here.
You have to share the proper screen if you've got dual monitors.
Yeah, I do, and I thought I was.
Charlie, it looks good, except can you see on the lower left of the screen, where can you see the screen that can you see the screen that shows all of this? Can you see this? If you look at my particular view, it's down in the lower left.
Let me get out of
the lower left is a button right over here.
Yeah.
You got to the left of normal mode.
Oh, sure, but I'm not in my PowerPoint because let's see why that's gone away. That's my trouble.
This high-tech stuff, you know.
Yeah. Okay. Well, now I've got something back, but it's not what you're. I'm not seeing what you're. You're not seeing what I'm seeing.
Your mouse is over the right thing. Move your mouse down to the lower part of the screen there, and
No, you're not.
Charlie, are you showing the nucleus slide? Is that what you
was.
want us to
Now
see?
I'm showing fission and fusion slide.
no, we're seeing the nucleus slide.
We're seeing the nucleus slide.
All right. Let me go to new. Let me stop share and do new share.
I don't see any slide.
No, but first you
Nothing now.
must hit
All
the
right. So
PowerPoint.
now I should get Microsoft PowerPoint.
Yeah,
Right.
before,
There you go.
That's what we need to see right
That's what it is.
All right. So I must have been.
there. Okay,
sharing.
let's mute ourselves and let them get started again.
All right. Okay, so here we are, just with that model of the nucleus. Bunch of protons, a bunch of neutrons in a very compact ball. The discovery was that if you had light nuclei and you put them together, they bound tightly and you got energy out. If you had heavy nuclei, uranium with 92 protons and 143 neutrons, and you broke it apart, you got out energy. And here's one of the points I wanted to make early on. If you want to have a chain reaction, it was interesting that before they even knew this physically was possible, there was the concept of a chain reaction. I told you last time that Leo Szilard had conceived of it and patented it. So here's the weird thing of a patented chain reaction, yet nobody knew how to make one. But with the discovery of fission, it became apparent that it might be possible, but it would require a situation like the follows. You have a uranium-235 nucleus, you put a neutron into that, it causes the uranium nucleus to split in two, releasing this 200 MeV, 200 million times what you associate with kind of normal room temperature effects. But if you want a chain reaction, you have to get out some more neutrons. And it was not clear that when you broke it into two fragments, you would break it into two fragments and get some more neutrons. If you did get some more neutrons, then these neutrons could go to making more fissions, and you would now have a multiplication effect. And it would go up exponentially. It would go up so that by the time you had had 80 of these generations, you would have reached a number kind of comparable to the number of hydrogen atoms that were burning in that picture of the Hindenburg dirigible. 10 to the 30 atoms, which again is a number it's just inconceivably large. It's a lot of things. Although turns out it is not all that much matter because atoms are small. Anyway, before you could go on to even think about making a bomb, you had to discover whether it emitted neutrons. This was done in about 1940. It's still not enough. You had to understand where those neutrons were coming from. Well, what was it that was breaking in half? Niels Bohr realized that it must be that it was not actually the abundant isotope of uranium. It was not the uranium-238 that was breaking in half. It was the uranium-235. One atom out of every 139 uranium atoms is uranium-235. That's a very small fraction. And yet that was the one that was breaking in half. People had a kind of muzzy idea of nuclear properties back then, but it became apparent that what was happening with the uranium-235 was it had an enormous affinity for slowly moving neutrons. It would, if you had a slowly moving neutron get very close to get adjacent to a uranium-235 nucleus, it would grab it and it would break in half. There are a lot of things that can happen when a nucleus takes up a neutron. It can just swallow the neutron and become one atomic mass unit heavier. It can bring in the neutron and send it back out. It can bring in the neutron, send it out just exactly as it came in. That's elastic scattering in the business. Or it can send it back with a little less energy. There are also, the neutrons can just miss and go away. So Jerry Slade asked last time, what is this idea of critical mass? And this is what the problem came down to. You could imagine establishing a chain reaction if you had multiple neutrons, such as is shown here in this picture. But you had to be sure they were confined so that they would go on and hit another uranium-235 nucleus. Natural uranium is mostly uranium-238. So in fact, most of these neutrons are going to hit uranium-238. They're not going to hit a uranium-235. Furthermore, they come out, they're traveling quite fast. They're energy of sort of 1 million electron volts. And they're going quite fast. And the likelihood of them being captured and causing a fission is small if they're moving fast. You can kind of make sense. They come in and go zip, they've gone by the adjacent nucleus, they missed it, or they just don't have much time to interact with it. So by 1940, they understood, yes, there are neutrons that come out of fission. They understood that it was U-235 that was doing the fission. And they understood that if you wanted to make a bomb out of natural uranium, some calculations said, oh, you need a bomb of 30 tons of uranium. So that's not a bomb, that's, it was a rough calculation though. So they improved the calculation. And it turned out, well, if you wanted to use natural uranium for a bomb, you might even get by with 14 tons instead of 30 tons. You do not put 30 tons or 14 tons in an airplane and go drop it on somebody. On the other hand, one interesting thing was that you could imagine that these neutrons, you could imagine putting together enough natural uranium in a building somewhere so that if you had enough neutrons and they were moving slowly enough, you could produce a self-sustained continuing chain reaction in which these neutrons would be slowed down so that there was this huge likelihood if they got anywhere near a uranium-235 in this block of natural uranium, they would interact with it. You could imagine, yes, it might be possible to make a power source out of it. You might be able to produce what today we call a nuclear reactor. So 1940, 41, this has worked out. But it's odd. They looked at the possibility for a long time of using what we call fast neutrons, which don't work very well with uranium-238, but they will cause fissions. Work with slow neutrons, which doesn't work at all with uranium-238. How about slow neutrons with uranium-235? Yes, that would work. But you know what? Nobody asked. Nobody asked, well, what if you used fast neutrons with uranium-235? That is, nobody asked that until two German refugee physicists in Great Britain, Rudolf Peierls and Otto Frisch. You remember Otto Frisch? He was with Lisa Meitner the day that she explained what Hahn and Meitner had described, had discovered that fission actually occurred. That was the discovery just at the end of 1938. In 1939, the whole world learned about nuclear fission. Anyway, Otto Frisch had by this time was left Denmark and was working in England. Peierls devised a very good formula for calculating critical mass. And he was a better formula than anybody had up to that time. And he applied it to uranium-238. Same answer as before, except now it was down to about 4 tons. You know, it was getting smaller, but it wasn't getting much smaller. Frisch, who, one of the problems these guys had was they were in Britain. It's now 1940, 41. Britain's at war. They're Germans. They're enemy aliens. They're at the University of Birmingham, where somebody has basically given them a place to get away from Germany. They're both Jewish. They're both out of Germany, out of the reach of the Germans early enough so that they're never threatened. But they're enemy aliens. So they can't work on radar, which is a big thing the Brits are all working on because of the London Blitz. So Frisch, who discovered fission with Lisa Meitner, is working on, well, can you separate the isotopes? Can you make uranium-235? Can you extract it and maybe get more, put it together into a lump of solid uranium-235? He's working on that problem because he has nothing else to do. But one day he thinks, you know, nobody has looked at what happens to fast neutrons when they come to the vicinity of uranium-235. So he takes and puts the calculation into Peierl's formula for critical mass. And the answer comes out 10 kilograms. And all of a sudden, it's a whole new world. 10 kilograms. I mean, even if you're doing rough magnitude calculations, 10 kilograms. You know, uranium's pretty dense. 10 kilograms is going to be a ball about that size. 10 kilograms is a real bomb possibility. Well, here's a nice story. They write up a memo. They say, geez, nobody knows this. We better tell the boss. Well, the boss is Mark Oliphant. Mark Oliphant is the head of the physics department at the University of Birmingham. And he's tied into the British committees, which are working on scientific problems of radar and things that are trying to keep the Germans from invading Britain. This is you know, the Blitz, everything bad is going on in Britain in 1940-41. You like ironies of life, they write a memo in which they describe fairly vividly what such a bomb might do. And they pass it on, as well as the feasibility of the bomb. They pass it on to Mark Oliphant. Mark Oliphant hands it on to the Tizard committee, and the Tizard committee sets up another committee to look at this. And they say, oh my God, this is real. This is really possible. And of course, because Peierls and Frisch are enemy aliens, they're not allowed to read their own memo. Their memo has been classified so that they are not allowed to read it. But the British are an adaptable people, and rather quickly they make British citizens out of Peierls and Frisch. And so then they're allowed to read their own memo again. Anyway, all this while in America, they're going on the development of some stuff to try and see if we can make, let's see, now, can I make this advance? Yeah, oh, wrong way, sorry. So this is just I'll skip this one. This is about fission and the things that come out of it. We'll maybe talk about it a little bit more later. This is the chain reaction idea, and you can see the idea is that you have one neutron come in here, U-235 breaks into pieces and gives off, in this picture, 3 neutrons, and they go here. And now you get this multiplication of neutrons and fissions. That's your chain reaction. That's the basic idea. Einstein and Szilard write their letter to FDR in 1939, warning him that there's these possibilities. Roosevelt sets up what's called the Uranium Advisory Committee. They don't do much. Vannevar Bush has left MIT and come to Washington to set up, well before we're in the war, he's come to Washington to set up organizations to coordinate American science. He asks Compton, a very distinguished physicist, to lead a committee of the National Academy of Sciences to review the stuff that's going to the Uranium Advisory Committee. Compton, a pacifist, raised in a pacifist tradition, a Mennonite tradition, sees what's going on, but says, you know, what everybody says, oh my God, this is a real possibility. It's not a very complicated possibility to imagine. The Germans must surely imagine it too. What if they get the bomb before we do? The only defense against such a weapon, and this is an argument you'll have heard year after year since then, the only defense against such a weapon is another weapon like it. So that if you use it on me, I'll use it on you. It's the deterrence argument right away, but now as secrecy gets involved, the deterrence argument is, of course, a motivation to work like hell to get your own bomb, because you're sure the enemy is secretly getting his own bomb. And that was a major motivation for a lot of scientists who come into the Manhattan Project. And it was a major for all of these people. But here is the leadership of the scientists in 1940. And you see on the left, this is Ernest Lawrence. I'll mention him again. This is Carl Compton. This is Arthur Compton. Arthur Compton is the person who, for the National Academy of Sciences, is telling Bush, this is real. What you've got here is a real possibility. This is Bush, Senator Bush. This is Conant, James Conant, who was president of Harvard and goes to work, is really, in a way, working for Bush. He's heading the committee, which ultimately is the committee that will drive forward the American project. And this is Carl Compton. Oh, Conant is, I said, president of Harvard. This is Carl Conant. Carl Compton, president of MIT. This is Arthur Loomis, a businessman, very wealthy, but in a way an amateur scientist, but serious amateur scientist with his own labs. These are the kind of people suddenly who you see here who are making the decision. Lawrence turns out to play a very important role because, as I was telling you, Piles and Frisch have shown that for the first time, a real bomb is a real possibility. And they tell Oliphant, their boss, Oliphant now has the role of trying to convince the Americans that this is actually something they should take seriously. For one thing, it's perfectly obvious that the British cannot possibly do what's necessary to make such a bomb. They're in the middle of a war. Their resources are strained to the utmost. There's only one country in the world that can make a bomb. And you know, I think I made the point last time, as soon as fission was discovered in 1939, every major country in the world, Japan, Germany, Russia, America, Great Britain, France, they all understood immediately that there was something here, that there was a possible bomb. Okay, Conant is in charge. Now, this is Szilard, who earlier than anybody saw the possibility of a bomb and was instigating the letter that came from Einstein to FDR. He's talking to Ernest Lawrence, and I put the picture up here so that you'll appreciate the following little story. There's an exchange between Britain and America. The so-called Tizard Committee comes to America and shows America that they're way behind in radar development. They have the magnetron, which will the tool that will generate radar frequencies. And we don't know anything about that. So that's news to Americans when it comes to the American science establishment. We have an exchange. Conant goes to England just about the time that Oliphant is getting the word on the possibility, the real possibility of a nuclear weapon. And so Oliphant tells Conant. Conant comes back. Then another American scientist, Charlie Lauritsen, goes over, and he actually goes around and talks to the various nuclear physicists there. He is himself a nuclear physicist, and comes back. So you have Conant, and you have Lawrence is telling Bush, this is real, we've got to do something. And nothing happens. Oliphant comes to America to say to Bush, come on, you got to do something. Now, Oliphant has the insight to go and talk to Lawrence. And that's why I want you to see Lawrence. He says, talk to Lawrence because he knows Lawrence is a very aggressive, energetic physicist. Lawrence has the Nobel Prize for inventing the cyclotron. And indeed, he loved big machines. He loved raising the money that you needed to build big machines. And getting Lawrence activated, energized, and realizing, oh, a bomb's got to be built. That was an important step because Lawrence goes and leans on Bush. They actually come very close to having Bush throw Lawrence out of the whole project because Bush doesn't want any kind of challenge to his authority. But in the end, what we have is, go back one. Whoops. In the end, we have Lawrence very actively engaged in this project and getting everybody else to go. So that by the end of 1941, Bush is on board. Bush is pushing for a major thrust by the Americans. We're going to have a project. And pretty much what Bush recommends, FDR goes with. So at the end of, in fact, he has a meeting, I think, scheduled on December 6th, 1941, to set up the organizations that will now push forward. Well, December 6th is not a day that will live in infamy, but December 7th is. And so 2 days later, 3 days later, we're in the war. We've declared war on Japan, and Germany has declared war on us. And so then we suddenly, there's a whole new level of interest in what Bush has been talking about. There's got to be some more developments, though, before we go forward with the full-scale engineering projects that are the Manhattan Project. And this is in part because it turns out that people realize, again, quite early, there are two possible ways to get a bomb. One way is to extract uranium-235 into such a density that you can have your, what Frisch was calculating was for pure uranium-235, a 10 kilogram mass would be a critical mass and could make a bomb. That's one way. But the other way is related to something else that was going on at the time and which people were waiting on a little bit. Fermi, and again, Szilard, thought that you might be able to make a self-sustaining reaction with natural uranium if you could figure out how to take the neutrons that are coming out of the fissions and slow them down. Because then the probability of them interacting with the other uranium-235, even though they're sparsely distributed through the uranium-238, that possibility goes way up if the neutrons are slowed down. This is where the idea of the moderator comes in. Uranium-235 splits, it produces 2 neutrons, 3 neutrons, something like that. It often depends, it varies. And these it turns out that these will be enough to make a continuing chain reaction if you can slow them down properly. So now you have really your first design of a nuclear reactor coming out. The idea is Szilard and Fermi, mainly Fermi has the vision for this. They realize that you might be able to use carbon. The thing that's very nice about slowing down neutrons is you'd like something that's fairly light, because the idea is that the little neutron is going to bounce off the moderator and so give some of its energy to the moderator, and it will then be a slower one, and it will bounce again off something, it'll bounce again off something. And it really turns out that only 4 or 5 bounces, and these neutrons are now down at a speed which is so slow that the possibility of interacting with U-235 goes up by a factor of like 500. And it's an enormous enhancement. but you got to have this multiple collisions slow down. And another thing that can happen is that it can bounce and bump into something and be absorbed. So you got to be sure that whatever it is it's bouncing off doesn't actually want to absorb a neutron. Turns out pure carbon is actually would be perfect because it's the same mass as a neutron, and the collision between them, the neutron gives its energy to the hydrogen, and the hydrogen is gone, and so it takes very few hydrogen to be a great mass, and hydrogen will capture a neutron and become a deuteron. Great. You could, and this was also water, your H2O, is made not with hydrogen and oxygen.
Audio problems.
He's fading in and out.
Yeah, Charlie had said he was having some difficulty before. Charlie, I can do the slides for you if you want.
Charlie's microphone is off.
Yeah.
Charlie, can you turn on your microphone?
No, Steve, well, I can, but
I got
you
it.
are uninvited by the host. I got to be invited by the host. It says I've been uninvited.
That may be the truth of our times.
Hello? Can you hear me?
I can.
No.
You're good now, Charlie.
You can hear me.
Yep. We can hear you.
Correct.
Yeah. I think I'm having internet troubles.
Yeah, hearing is good now.
All right.
Could you
But
review the
now I
carbon? Could you review the carbon slowing again with the hydrogen? We missed a lot of that.
All right. Let me see why I'm not. I don't have any. Oh, I see what I got to do.
Your voice is good.
Okay. And you got a picture
Yep.
of Enrico of Fermi? You should have a picture of Enrico Fermi, have you?
Correct.
Okay. All right. So say hello. All right. So this. I'm not hearing you, Steve.
You're all set, sir. You may continue.
Okay.
Please,
All right.
everybody else, please mute your microphones. Thank you.
I think you can mute. All right. Anyway, this is so Fermi. Jerry was asking me to repeat what I had to say about bouncing neutrons off carbon. It turns out carbon-12 does not particularly like to pick up neutrons. So you can bounce them, the elastic scattering. Hydrogen does like to pick them up. And so if you decide to use water as a moderator, I've actually built a small, what's called subcritical reactor, and we used water as a moderator. Remember, the goal is to slow them down. But if you were to use heavy water as a moderator, that would be outstanding, which leads to some stories, because it was clear the Germans understood this because they were trying to capture supplies of heavy water that existed in Norway. And then, of course, they did conquer Norway. And the Allies made several, one quite disastrous raid to try and destroy those supplies of heavy water so that the Germans couldn't get them. In the end, they succeeded. It's a nice story, but I'm not going to tell it here. Anyway, that's the idea of the moderator, is if you slow down the neutrons, you might be able to make a sustained reaction, chain reaction with natural uranium. And that's what this is a picture of, because on December 2nd, 1942, see, we're into the war, it's a year later. Fermi and Szilard had been working at Columbia first, building piles of uranium rods and spheres and cylinders in amongst blocks of carbon. And you know, you built the thing, it was a great big pile. And that's where the term came from. These are world's first nuclear reactor is built under the football stands, the no longer used football fields of University of Chicago because they had given up football to the horror of much of the American public. This was a very exciting event in which adding block by block more uranium to this very large structure, you could watch the neutron flux rise, and you had really the fundamental elements of all subsequent reactors are here, because the idea was you didn't want this to run away. You know, for one thing, you're building it in downtown Chicago. It would be nice not to have a Chernobyl in the middle of Chicago, but also, also you didn't want to irradiate yourself. So I mean, here are these people down here. So you get a sense of this is kind of the multi-ton structure that will produce a sustained reaction, chain reaction with natural uranium. And you see the scientists are supposed to be up here in the balcony watching. And this guy down here, he has got a control rod. He's got a rod of cadmium, which has a very high probability of absorbing neutrons if there are any around. And the idea was if you see this thing starting to run away, you shove the cadmium rod in, it absorbs neutrons, and now there aren't enough neutrons in the chain reaction to sustain it. Basic control features of all reactors since. But this is the first one. And the reason it's a drawing is because nobody thought to take a picture at the time. There was no photography. So all we have is what people remember. And that's kind of statement. All right, it's now 1942. And in September of 42, Bush and everybody, I'll tell you, I lost the thread. I'll pick it up in a minute. So Bush is saying, let's go. But clearly what we're going to need to do is we're going to need to separate U-235 from natural uranium. Anybody who could do the calculation saw this is a huge task. This is an industrial task of a magnitude no one had really ever attempted. Furthermore, there's another mode, I was saying earlier, there's another way to get to a bomb. And as I'll show you in a minute, it too was going to be an immense industrial task. You needed to put this in the hands of some group that could, in secret, build an enormous industrial infrastructure. And in fact, they're going to build 3 cities to do this job of building, in the end, 3 bombs. But they've put in charge Leslie Groves, who was promoted to Major General. He had already done something big. He had directed the construction of the Pentagon in 1941 to 42, and they in charge of the Manhattan Engineering District in 42, 46. So he is the military man. The Army is given the job of directing the work that's necessary to be done to build a bomb. The physicists never liked Groves. He's an Army man. He gives orders. People are supposed to do what he says. I think he was absolutely central to the success of the program. He had an immense capability of making decisions quickly, and he was willing to be wrong. He thought, and he actually told other people, look, if there's more than one way to do something and you can't decide which is better, do them both, but get going and do them right away. As an example of doing things right away, the Manhattan Project had been decided on in like June of 42, but not much had happened until Groves was appointed. But one thing that happened was somebody was saying, you know, we ought to get some land in Tennessee. There's 52,000 acres in the Clinch River area of Tennessee. We ought to get that. And yeah, it was on their sort of to-do list. So Groves was appointed to the job of heading this project on the, I think it's on the 16th of September. Then on the 17th of September, he buys the 52,000 acres of land. And now we're going to displace the personnel that live, the people who are living there. I mean, these are not empty acres, but he's going to do it. The next day, he buys a large supply of uranium that has been stored on, of all places, Staten Island. And he's called to a meeting with the Chief of Staff, George Marshall, and the Secretary of War, Stimson, and his superior generals. And he goes to this meeting in which they set up the organization. He's going to be supervised by a committee that has some civilians in it. They propose 9 members. He argues them down to a 3-member committee. So it's basically going to be Bush with Conant as his alternate, and a general and an admiral, as it turns out. And Groves then says, and I love this, he says to the Secretary of the of War and to the Chief of Staff of the Army, sir, may I be excused? I need to leave Washington immediately to go and inspect the 52,000 acres that I have just purchased in Tennessee. And off he goes. And that's kind of the style of the man. He is going to get things done, and he's going to have to build 3 cities to do that. And there they are. Whoops, back there. There's my 3 cities. He's going to build a city at Oak Ridge. He's going to build a city at Hanford. He's going to build a city at Los Alamos. At Oak Ridge, he's going to build a city which has several jobs. But its main job is to extract U-235 from natural uranium. And you'll see in a minute kind of what that takes. Out here in Hanford, in the desert lands of eastern Washington, at a big bend in the Columbia River, he's going to build another, essentially, city. And then at Los Alamos, he's going to build yet a 3rd city. This city is going to make uranium-235. This city is going to make plutonium. And plutonium is this other route to a bomb that I spoke about before. He's going to, and then both of these sources of material send their supplies, uranium-235 from Oak Ridge, plutonium-239 from Hanford, come to Los Alamos, where a cluster of very talented physicists led by Robert Oppenheimer figure out how to put the stuff together to make a bomb. I mean, it's all very well to have a critical mass worth of the stuff, but somehow or other you've got to assemble it into something that explodes. And this is not easy. So that's what you have. You have 3 cities coming here. And there was actually a 4th element, not really a city, but in Chicago there was something called the Met Lab, the Metallurgical Laboratory. This is kind of like the radiation laboratory was named the radiation laboratory, so nobody could tell what it was doing as it was developing radar. Well, the Metallurgical Laboratory was named the Met Lab without telling it, so it wouldn't tell anybody. What they were really doing was, first of all, making that first self-sustaining nuclear reactor. And secondly, they had begun to work on this second route to the bomb. And let me explain about that second route to the bomb. Again, it was recognized fairly early. You can build, if you can get U-235, you can make a critical mass quite easily. But separating U-235 out is difficult because it is chemically the same as U-238. So you have to find some kind of physical separation, some method of doing physical separation that is sort of delicate enough that it can tell a mass of 235 from a mass of 238. And that's very tricky. That's not easy at all. But someone had already noticed that if you had a nuclear reactor, that a lot of those neutrons that you're losing because they're getting absorbed by uranium-238 and not going to make more neutrons with uranium-235, those neutrons were actually turning uranium-238 into something that, on kind of semi-theoretical grounds, already by 1940-41, people were saying, you know, if we could get this stuff, if we could make this stuff and get it out, then we could chemically extract it from uranium-238. And that would be a lot easier to do. And then we could build a fission weapon from plutonium. Well, a lot of unanswered questions, partly because there wasn't any plutonium-239. It does not occur in nature. You have to make it. It turns out, though, that what's happening in a nuclear reactor is all the time you're making it. Your neutron goes into uranium-238, and that adds one nucleon. So if you go from being 239, you go to be 239. The neutron emits an electron, and so the neutron becomes a proton. So it doesn't change the mass number, but it changes the proton number. It changes you into neptunium. And the neptunium emits a beta ray fairly briskly, and that doesn't change the mass number, but it changes into plutonium-94, which turns out to have a fairly long half-life, some thousands of years. So you can now say, oh, you know, I could chemically separate plutonium from all this other stuff. Well, there's a lot of other stuff because there's a lot of fission going on all the while because you're making this in the same block of material in which the other neutrons are causing uranium-235 to fission. But this is tempting. If you can actually make enough plutonium-239, you can make a different sort of bomb altogether. Glenn Seaborg is the leader in doing this. In the 1940s, he, working with Lawrence's cyclotron at Berkeley, makes the first plutonium-239 and identifies it. It's an invisible amount, and you could tell it's new and that it's plutonium-39. Well, you could tell that it was different from other things in your sample. You bombarded uranium with neutrons, and then you looked at what alpha particles came out, and you looked at the energies of the alpha particles. And all of a sudden, you would be seeing alpha particles of an energy you had never seen before. That was your clue. There's something new there. There's a new element there. He does the chemistry. He shows that, yes, there's something new there. And by the time he's done identifying that this is a new element, that it is got a half-life that's long enough so that it can hang around and be made into a bomb, there's now, people are beginning to decide we can go this route. He moves to the Met Lab from California and works at the Met Lab where he's developing the chemistry that will be necessary to separate the plutonium from the regular bomb. All right. Now, you're going to do this, all right? We've had one reactor. We have the pile of graphite and uranium that Fermi put together under the football stands of the University of Chicago. Well, people, as I said, realized that's probably not a great place to do this kind of research. So they moved the Met Lab south of Chicago to Palos, Illinois, and called it the Argonne. It's now the Argonne National Laboratory. But there, they do some more reactor building. They build two more. Well, first of all, they move the Chicago pile 1 down there. They build another Chicago pile, graphite pile. They build another pile. They're doing this in months. But all right, so here is the X10 test reactor designed at the Met Lab. Now, again, I want you to get a sense of what's going on here. I mean, these are big items. They're building this because it's within a month of the successful testing of Fermi's reactor in Chicago under the football stands. Groves has acquired 500,000 acres in eastern Washington, where the plan is we will build 3 huge reactors whose job will be just to make plutonium. These are going to be multi-hundred megawatt reactors, but you're just going to dump the energy. All you want out of it is the plutonium. Now, I mean, think of this both as kind of gutsy leadership and gutsy engineering. Nobody's built a reactor before. Nobody has ever done reactors on this scale before. The only reason they think it'll work is because Fermi has got his work with his little 1 kilowatt reactor under the stands in Chicago. And this is Groves saying, we're going to do this. If we're going to do it, we're going to do it. We're going to build 3 huge reactors. We're going to have to develop massive ways of doing radiochemistry. The products that come out of these nuclear reactors are extremely radioactive. You've got fission fragments, which are red hot. They decay fairly quickly, so the worst of the radioactivity goes away within a few days. But you have to have a way of extracting all this and doing chemistry on all this without killing the people who are doing it. And this is a whole new idea. I mean, nobody has done this kind of chemistry before. So they have to invent it all. In the meantime, they have to build Hanford Works. At peak construction, there are 50,000 workers there. You know, this is in the middle of a war. Holy smoke, it's big stuff. All right, so Groves leads this. Now, another thing which Groves does, which I find very impressive, is he chooses Oppenheimer to be the director of the actual bomb invention and construction that is going to go on at the third city, at Los Alamos in New Mexico. And he does this really against the will of all the Army intelligence services, because Oppenheimer, he comes out of Berkeley. His former girlfriend, his wife, and his brother have all been members of the Communist Party. He is absolutely known to have been sympathetic, but probably was not a member. The Army is intelligence just is in dudgeon, and Groves says, "No, I want Oppenheimer." My friend Dan Klepner tells me that his thesis advisor was Norman Ramsey and was friendly with Groves. Said he thought Groves liked Oppenheimer because Oppenheimer could explain things to him so clearly. Whatever the reason was, turns out to have been a fantastic choice. And it's, again, I think very much to Groves' credit that he would do this. Furthermore, Oppenheimer then had to face down, or convince, maybe a better way to put it, Groves that they should, at Los Alamos, have a community of scientists which were not compartmentalized by jobs, so as you would want to do to maintain maximum secrecy. He wanted a very open, communicative community of scientists. I mean, they were behind a barbed wire fence, but so they're not going to go out of Los Alamos. But he wanted everybody to know what everybody else was doing. This turned out to be crucial for the success of what they did at Los Alamos. And again, Groves accepted that. He took Oppenheimer's suggestion. So Groves was much disliked by physicists and also by many of his subordinates. And yet, his chief subordinates, Kenneth Nichols, said, he was Groves was a bastard, but if they were going to do this again, I would work for him before I would work for anybody else. So there was just a little summary of the personality of Oppenheimer. I found Dan Klepner's remarks about what Norman Ramsey had to say very interesting, because Oppenheimer was famously said to not suffer fools gladly. And these would be physics fools, if you, I would not be eager to talk with him if he wanted to find out what I was doing. I would be I would be nervous. Anyway, Edward Teller talks about Oppenheimer as incredibly quick and perceptive in analyzing human as well as technical problems. And that is true. And I'll maybe give you an example of that a little later. All right. Here's what we do. We got to build a city. We're going to build Oak Ridge, Tennessee. There's nothing there. There's no roads. There's no bridges. There's no power stations. There's no railroad tracks. There's nothing. You got to build the infrastructure, and you got to build the city, and you're going to start just at the beginning of 1943. You got to do this whole thing, and by the time you're done, it turns out you have to build living quarters because there's not enough around that part of Tennessee for people, and you have to build some of the largest plants that anybody has. Up to that time, the largest single-roofed building, I don't know, in the world, anyway, in America, was the Pentagon, built by Leslie Groves. And now the largest roof building becomes something called K-25. It's the building in which gaseous diffusion is going to separate uranium-235 from uranium. All right, let me talk about why you have to be big. So here's the idea of gaseous diffusion, kind of rough. But you're putting in the feed, and you put the feed in through this unit. You have pumps. You're pumping it through this unit, and you have a porous screen, and with sort of millions of holes per square centimeter. Very fine. In fact, this was one of the major technical problems, was to make this so-called barrier. And you run through the barrier, and the idea is that out of one side of the barrier comes something that's slightly enriched in uranium, and you're going to do this through multiple stages. You're going to send depleted material down back through here and out this end, and you're going to send enriched product out this end, and you're going to use 2,892 of these things. And you look at the little diagram and the little pump, and you think, oh, that's nothing. But now look at the picture. Do we have, I guess we don't have a human being in this here, but a human being would stand about this high. This is big. And you need 2,892 of these. And there's a war on, you know. There's it's not easy to get these things. That was the other thing Groves did the day after he took over. He went to the guy who was in charge of priorities and said, give me a AAA priority. And the guy said no. And he said, I'll have Bush and the president talk to you. And the guy said, oh, okay. And gave him his AAA priority, so that he's buying all this kind of stuff. It's amazing. And you need 28,000, you need 2,800 of those. And so they go into a plant that looks like this. You know, this becomes the largest plant under a single roof in the world. It's about a half a mile from one end to the other. That's the K-25 plant. Still under construction in June of 1944. Now, there's another way to separate, and this is the way that Ernest Lawrence wanted to do. I remember I showed you last time a mass spectrograph where you send charged particles through a magnetic field, and the ones with small mass bend more in the magnetic field than the ones with big mass. Well, that'll work for U-235 and U-238. You have to figure out how to make a beam out of them, and it turns out they won't separate very much, but they will separate if you make enough. And so I think I remember showing you how things went around kind of in a circle, semicircle, and the two beams would come out. Say uranium-238 might come out there, but the uranium-235 would be bent and a little more and come out there. So this is one of those. How many of those do you need? You know, well, first of all, you need to stack them up. They have to have a magnetic field go through them. So you can't really tell here, but each of those, here are what we were looking at before, and those go in here. They fit in there, and so charged particles are being fed into individual units all the way around this so-called racetrack. And magnetic field goes, the magnetic field lines go circumferentially through these C's, these these calutrons, as they were named. But this was Lawrence's idea, and this is a kind of interesting story. Now, I'm not sure I can do what I want to do now. But let me try. What I want to do is I want to show you some consequences of what was going on at in building these Y12s. I mean, these are enormous magnetic coils. There has to be enormous windings of copper coils to make the magnetic field that is going to bend these particles in the semicircles from which are going to separate the U-235 from U-238. And let's see here. Let me see, next slide. Yeah. So, I don't know, how many of you remember 1943 pennies? I mean, it's quite a...
If you have a copper one, you're lucky.
Yeah, well, there weren't very many of them. And one reason was there wasn't much copper. There was this copper shortage. So one of the stories that I think is very interesting is that Groves went to the U.S. Treasury and said, we don't have enough copper. Lend us your silver. Well, the U.S. Treasury says, how much do you want? And Groves says, I want 14,000 tons of silver. The reply was, we don't deal in tons, we deal in troy ounces. And they actually had to work a little bit to figure out what the answer was. But in the end, Groves got from the U.S. Treasury 14,000 tons of silver. And the silver was wound into thin wires, which were made to be the coils of the magnetic field that was being used in the calutrons. That shortage of copper also showed up another way, if you remember 1943 pennies. See here on my desk, there are 5 pennies. And I have here in my other hand, is this coming through? Anyway, I have here in my hand a little strip of magnet. You see, if I put it down there, it picks up those 3 pennies, but not those. And you see, there was a copper shortage that year. And so you had steel 1943 pennies. And that was one of the reasons why Oak Ridge had to take 14,000 tons of silver from the U.S. Treasury and convert that 14,000 tons into silver wire, which has a conductivity that's actually better than copper. And so use that for winding the coils. So this is people operating these machines that could separate the uranium-235 isotope from natural uranium. And these are operators at what was called Y12. So there were 3 stages of this operation. And see, I'm not. My screen sharing. Yes. And so here's kind of a summary of, in January 1945, after 27 months, because I should tell you that they tried to do the separation with those those magnets, and they shorted out. It turned out they hadn't. There were all kinds of. I mean, everybody was in a hurry. And so they had to take down the magnets, sort of reprocess the silver with which the magnets had been wound, and then with a better design, put them back together again. And then they end up. They also picked up from the Navy, which was working on another form of diffusion to separate. They ended up then finally with 3 stages of processing. One stage was thermal diffusion, and you see a diagram like this, and it says, oh, you're putting stuff in here, and there's some isotope separation so that the lighter U-235 comes out up here, and the heavier U-238 goes down there. But the changes are very small. You need to have 2,142 48-foot tall tubes to go from sort of 0.75% abundance of uranium-235 to get it up to about 1% abundant. So you're building this huge structure to get about 1% enrichment. You need 80 to 90% enrichment. So you then run them into what your other idea was, which is the gaseous diffusion of, so it has to be in a gaseous form. It goes in as uranium hexafluoride, which is not lovely stuff. And it goes through a porous membrane. And the tolerances on these things are extremely small. And the plant has to be basically a half a mile long. And it becomes the largest single roofed building since the Pentagon was built. And then you run them through another set of buildings which have 864 of these tanks, of which we saw a picture in the previous slide, plus 36 more tanks of a somewhat different design. This is getting to be a huge stuff. And finally, out at the end, you get uranium enriched to a sufficient enrichment, about 85%, that you could imagine it making a bomb. This does not happen until essentially early 1945. The war has been going on all this time. And so early 1945, they begin to produce at what is essentially a couple of grams a day, a couple of grams of fully enriched uranium-235. And you need, as they understand it from their calculations and more experiments, you need about, of uranium-235, you're probably going to need 40 kilograms. So that would be 40,000 grams. So my numbers aren't right because they're on path, and I'm not sure why, but they're on path to make enough to make a U-235 bomb. In the meantime, they're also working on plutonium. And this is just a recap of what I said a little while ago, where you put a neutron into uranium-238, you get uranium-239, it decays with a half-life of 24 minutes into neptunium. You see it's gone up, I see it gives off a beta particle, an antineutrino, who cares? But in 2.36 days, it's turned into plutonium-239, which has this half-life of 24,000 years. So that, I don't know why I've got that there. Oh, yeah, it does decay back to 235 by making an alpha particle, but this is a half-life long enough so that that's not going to be of any importance. But Nagasaki, and I think that's interesting for the bomb. And you have these vast plants. This is one. There are actually 3 by the time we're done. They make this stuff. You still have to separate it. You have to separate it from exceedingly radioactive material. And there's another one of its plutonium-producing reactors. you're not using the energy for anything. You're just dumping the energy into the Columbia River, which is what's over here. That's the Columbia River. And you have the uranium tubes in racks like this, and they're being irradiated. They're a nuclear reactor. They've scaled up from the 1 kilowatt reactor at Chicago under the stands of the football field. They've scaled it up to something in the hundreds, several hundred megawatts. And I mean, these are real power reactors, and you can't get near them. So you have the slugs here, and you push them out the back into a water tank where they have to sit for several days so that the short-lived, extremely intense radiation goes away. And still handling everything remotely, you have to take them off and process them. This is engineering of a major sort, never tried before, and no pilot plans, basically that. And then the third site finally is Los Alamos. So these materials that you've been making at this place, they go to Los Alamos, where people are working. Here's just a picture to give you a sense of it. It's in the mountains. It's isolated. But you don't need to dwell on that. You have to explore criticality. People did things like this. You're trying to make sure that your bomb will go together and explode quickly enough, because one of the problems you have always is the criticality, the ability of the bomb to multiply its fissions to up to a significant amount. You need about 80 multiplications to get enough energy to do damage. And anything that gets in the way of those 80 multiplications will make it into a dud. So you have to somehow or other put, you don't want the fissions together long enough so that you can get 80 generations of neutrons causing fissions, causing more fissions, causing more. You get the multiplication. And you have to, you want to see how that works. So here is somebody who's working with a plutonium sphere. Actually, I'm not sure this isn't just completely simulated, because in 1946, somebody died as a result of this kind of experiment. You see, you've got plutonium is the idea here, and a smaller sphere of plutonium there. He's got it kind of wedged here, and he's got a screwdriver, and he's getting it closer and closer together to make a critical mass, a mass where the neutron multiplication runs away as it would in a bomb. And of course, the story is, in actuality, this happened. Something slipped, this dropped out, the bomb, the thing went supercritical, and he had to pull it apart because there were other people in the room, and he died miserably a few weeks later. This is somebody who just sort of recapitulating that. Anyway, the plutonium bomb turned out to be much more of a problem than the uranium bomb, because plutonium is more fissile. It wants to break up. It wants to get its energy away. And so you had to do a whole new design and of implosion with conventional explosives. So you had to have your uranium down here. You had to have something here which would produce a neutron source. And then you had to have explosive lenses around your uranium, around your plutonium. And the idea was that you exploded these things, and they're designed so that they focus the explosion inward, and they drive this hemisphere of plutonium down to a density which is critical, and they then the neutron source detonates the thing. I don't know. So here's the test. Here's Trinity. Here's July of 1945. Here's SED, Special Engineering Detachment, Herbert Lair, Army man, with plutonium core for a Trinity bomb. And I think you should see, I hope you can see, that's the bomb. That's the plutonium core. On the other hand, this is what it has to go inside, something like this. This is instrumented for experimental reasons. So one you actually drop would not look quite like this. But this is what the explosive consists of, and this is what the explosive will do. All right, we're coming here to the exciting point. This one you had to test. You had to test the plutonium bomb because you had to invent the explosive lenses that would focus explosion inward and drive the plutonium down to its critical density. And this test was July 16th, 1945. So next month will be the 75th anniversary of the first nuclear blast at the Trinity test site in Alamogordo, New Mexico. Now, the story then unfolds pretty quickly from there. Yes, one of the things that you get is you get fusion. And so I thought maybe I could go back here. I don't know. Maybe if we have time, I'll come back here and show you a piece of the fused material, the fused radioactive material called trinitite that was created by the explosion of the bomb. I have a sample here. I was going to show it to you on my phone, but it'll take me so long to change over to my camera that I think I'll just go on. Trinitite blank. Pick the targets now. That's just the end game. There were by this time, strategic bombing had essentially given up because it turned out strategic bombing was not very effective. And so Curtis LeMay, who was leading the Army Air Force bombing planes and program of bombing, had moved to essentially massive bombing. We were trying to destroy cities and break will. They bombed Tokyo with 334 B-29s, dropping loads of conventional explosives on Tokyo. They bombed other cities similarly. They did not bomb Hiroshima. They did not bomb Nagasaki. There were a set of cities that were reserved. They were reserved to be able to see the effects of an atomic bomb, of a nuclear weapon. August 6th, they flew what was called a little boy bomb of uranium-235. It was detonated by having a slug of uranium here, a slug of uranium here, such that the combination of these two would be supercritical, and you combine the two with an ordinary explosive here, which drove the uranium-235 into the sill. And it all hung together long enough to generate about 80 generations of multiplication and produce an amount of energy in the bomb, which was equivalent to about 20 kilotons of TNT in one bomb. It was a startling event. There it is in the bay of the Enola Gay on August 5th, 1945. They're asking for the go. They got the official go for bombing on the 25th of July, and Truman, who was away. Here it is. And this is just a short movie of the bomb. So the team that dropped the bomb was practicing dropping dummy bombs in Nevada. And they had a maneuver. You dropped the bomb, and then you dove kind of towards it to get up to airspeed so you could bank and get away and get about 10 miles away. And then you see the picture being taken. I don't know whether this is from the observer plane or from the actual plane that does the dropping. Then you see the kind of jiggle here. They've lost the top of the mushroom cloud. And now where is that? There it is. We're getting back to it. They lost it because they got hit by the shock wave coming from the bomb. And it jiggled the plane and knocked them out of alignment. Now here we are back with the classic mushroom cloud. And that was Hiroshima. And And this is what it looked like on the ground. 1.2 kilometers from ground zero. The devastation is extraordinary. Somewhat more than 100,000 people died in that explosion. Somewhat more than that died subsequently of radiation sickness, which was widespread. Somewhere, the death toll probably ran around 150,000 people. It's an extraordinary number, but in fact, conventional bombing with incendiaries, such as used in Dresden, but particularly used in Japan by LeMay and the B-29s, was already reaching numbers like that. The difference, of course, was this was only one bomb from one plane. Fat Man, which is the plutonium bomb, was used on Nagasaki 3 days later. And it killed somewhat more than 45,000 people, not as much as died at Hiroshima, because the city was protected by some hills that kept the bomb from spreading. It was a bad thing. You want to know how much it cost? Today, it would cost you $38 billion. Back then, it cost you less than $2 billion. That's kind of the difference between the dollar then and the dollar today. And Niels Bohr said, humanity will be confronted with dangers of unprecedented character unless in due time measures can be taken to forestall a disastrous competition in such formidable armaments and to establish an international control of the manufacture and use of powerful materials. Well, due time seems to be a long time. It's 75 years, and we still haven't got it. I recommend you read Rhodes' book. Thanks.
Someone posed a question on chat earlier about how much the Japanese and/or Germans knew about what was going on at Los Alamos.
Well, I can't answer that question fully. The Russians clearly knew a lot. I think we now know there were approximately 24 spies working in the Manhattan Project. Different. But here, my last slide, raises that same question, John. Secrecy, how effective? Secret from whom? We sent a mission into Germany in April. The war ended in Germany in early May of 45. I think I don't think the Japanese and the Germans knew what we were up to. Oh, well, they knew we were up to something because it was obvious. All of a sudden in 1940, all the physics publications stopped publishing anything about neutrons and uranium. And people, Japanese commented on that, the Germans commented on that. It was pretty clear something was going on. And the secrecy, I would say, I posed this. I thought we might have some time for a discussion, but I was going to do some breakouts maybe and have people think about these things. But the secrecy was not effective from the Russians. The Russians knew pretty much what was going on. They had David Greenglass, and we had several. Well, we had the Rosenbergs who were tried and executed for what they did. And there were a couple of people who were never tried and who just walked away from it because to have tried them would have required revealing things we didn't want to reveal. So I always thought the question of secrecy and secret from whom is answered. It was mainly secret from us. It was mainly secret from the United States and from its political authorities. There was never any congressional discussion. In a democracy, you're creating something which is changing the world, changing the situation of our country in the world in an enormous way. And I'm not saying we could have done it, but we didn't do it. It was secret from the American people. Groves also kept secrets. One of the major motivations for the scientists working on this program was to have a deterrent against a German bomb, which, you know, we knew in principle they were quite capable of producing. And so in April, Groves sent this committee called Alamos. Alamos is a Greek word meaning grove. It was bad secrecy technique, but anyway, they did it. And they sent it to Germany, and sort of right along the battle lines and even across. They were capturing Heisenberg and other leaders of the German physicists, and discovering in April that no, the Germans had never done much. They had tried to build a nuclear reactor, but they hadn't ever got one really to work.
There was an excellent play about 3-4 years ago done in Cambridge on the capture of half a dozen German scientists and their interrogation. That's not really the right word. In Britain, in a rather nice little castle, as I recall.
No, it was Farm Hall, and that was that was a good play. I took my class. I was teaching a class on the history of the bomb, and I took my class from upstate New York down to New York City to see that play, because it's really quite an interesting play. But that was where we were learning, and of course those Germans who were being interned at Farm Hall, they were shocked to find that we had made a bomb and that bomb had worked. And then they realized that they had the moral high ground because they hadn't made a bomb. They just only wished they had. But also,
Charlie, can I ask you a question?
Please.
Well, first, let me just say, one of my patients worked on the timer to the detonator for the first bomb because he had to make it go off at a certain altitude.
Right.
So he worked on the timer to the detonator. But right. You said the source of neutrons. What's the source of neutrons?
Well, there are a lot of different sources of neutrons that you can have. The one I used, it turned out to be a little bit of, the one they probably used was some radium mixed with beryllium. If you have radium, the alpha particles come out of the radium, and they interact with the beryllium, which then makes neutrons, emits neutrons. That would be one possibility. And that was what they were using. We actually used, in my laboratory, we used plutonium with beryllium, but that would never have been used at this time because all the plutonium was going to make a bomb.
What does the alpha particle destabilize the nucleus and then a neutron comes out?
It turns out beryllium, beryllium is very prone to make neutrons that way.
I see, thanks.
Actually, beryllium is also used in the moderators too.
In the what?
I say beryllium is also used in the moderators too because it is such a great, using it, it's light and because of the neutron generation that you can elicit from it. So beryllium is a very important component. One thing I might add is that Los Alamos, one of the big things they were doing at Los Alamos is working on these lens high explosives. That was one of the big things that they just had to get down right. And it was really a tough project, a tough problem. So you had a lot of explosions going off at Los Alamos.
It was a huge rush effort because they had thought at first they could use something like they used with uranium-235,
right?
Use the gun mode. But it turns out that plutonium-240 is an impurity that comes along with your plutonium-239. The plutonium-240 is spontaneously fissions. It just breaks apart itself and gives off a couple of neutrons. So that impurity is going to produce a premature detonation as you try to bring your lumps of plutonium-239 together. And the way you get around that is what they did. You have to just power them together really fast, and then that bomb doesn't hurt you.
Exactly. And that's part of the detonation scheme also. You have to time it like... But
they thought at first.
Timing is important.
That was a crash effort. I mean, they thought at first we're not going to be able to do it, but you're right. I mean, it was a very big dance. And,
the use of beryllium is interesting because I think that's how the bombarding beryllium with alpha particles is how neutrons were originally discovered by Chadwick.
I guess you're right. Yeah, I hadn't remembered that. But yeah, because he discovered it with a radioactive source. He didn't discover them with an accelerator. So I had this slide. I thought, we talk about what happened. One of the things I think is very interesting about fission is it was absolutely discoverable as early as 1933. As soon as you had neutrons, people were looking at fission in their laboratories and didn't know it. And, and you can think, well, what if they had known it? What if they discovered fission in 1933? That's one thing. I think that's an interesting question. And it was absolutely practical. It was sort of the lack of a prepared mind. Nobody was thinking that there was such a thing, and so nobody looked. And not only that, when you did look, it was astonishingly obvious. Bohr brought the news from Europe in 1939 that Hahn and Strassmann had seen fission, and Meitner and Frisch had explained it. He brought that news to Washington to a meeting of the American Physical Society. And that night they just rushed out to, one of the nearby laboratories. And there's a picture of guys in three-piece suits observing nuclear fission in the laboratory. I mean, it's dead simple to see once you know what to look for. And then here's another question that I wondered about. Oh, what if the bomb had been ready 6 months earlier?
The answer is you would have had steel pennies a lot earlier.
Well, I don't know, Jerry. I think the question
by earlier, do you mean for example, January of 1945?
Yes.
I think you would have had one city less in Germany.
Well, I wonder about that. I mean, there certainly plenty of racism in what we did.
Well, there was, but there was also a letter from the scientists, from a subset of scientists at Los Alamos, saying, "Don't drop the bomb on Japan. We worked on the bomb in order to use it on Germany."
No, we worked on the bomb to deter. We didn't work on, that was what their position was. We didn't realize it was going to be used. So I forgot to hit the conclusion to my point about Groves and the Altos committee coming back saying, now the Germans didn't do anything. He just put that report in his safe. He didn't tell any of the scientists. It was April.
But I believe the scientists, though, were intending to use it on Germany because a lot of them had immigrated, were Jewish and so forth. And that was their intent. And I think in the
letter,
book, in the book by Oppenheimer, it's kind of brought out there that they wanted it on Germany. They really didn't want to use it on Japan.
Correct. And they wrote a letter
Yep.
specifically pleading that it not be used on Japan. There was a whole subset of the scientists, not all of them, of course, but a whole subset signed this letter.
It was a rather small subset. I mean, they were significant people, but already people, I think Joseph Ruppblatt, as soon as he knew that the Germans hadn't got anything, he just pulled out of the project. He went home to Britain. And other people also. So in a way, the point I wanted to make about Groves, putting the report in his safe was that he knew that it would sort of cause the scientists to work less hard on what they were doing if they knew that, and he wasn't going to have that.
I took a course on Truman a few years ago, and one of the major discussion subjects for a whole class was how many Americans and others would likely be killed trying to capture Japan, particularly the way the Japanese soldiers were defending to the death all the islands on the way into Japan and then presumably at Japan. One of the estimates, and no one knows whether it's accurate, one of the estimates is that we would lose 750,000 soldiers to capture Japan. And that was, as I understand it, the strong argument to use the bomb.
I think you're absolutely right. I mean, we were going to do that. I worked out in California one summer on a project, and it's at SRI. It was a think tank that had once been the Stanford Research Institute, but they had to drop the use of the name Stanford, and they had a large area of buildings that we used for recreational purposes, but those buildings had been built as hospitals in 1945 for the expected casualties that would come back from the invasion of Japan. They were never used.
Yeah, you know, that's true. When I was younger, I saw a documentary and some other stuff about Japan, and there was a group of people that worked for the emperor, and it turns out these guys were absolutely fanatical because the emperor wanted to, stop all this killing, and that was when LeMay was really bombing the hell out of Japan, and then when the bomb came along, and just in a matter of one day each, knocked out 2 whole cities, it still took some convincing for the emperor's terrorists, if you want. They were protecting him to get the emperor. Well, actually, the emperor came out and he said, "We got to stop this war." Yeah. Go ahead.
I think
It was a couple of days between the 2 bombs.
What?
So an opportunity to stop the war after the first bomb, and after the second bomb, I believe it happened almost instantaneously.
Well, 3 days later.
Right.
Almost instantaneously.
Right.
Yeah.
Were the Japanese warned a priori about the atomic bomb, the first one being dropped?
No.
Were they notified?
I don't think so.
Really?
Not either one.
Neither
But
one.
they were
Oh, I
more-
thought pamphlets were sent down somehow.
Yeah.
Okay.
After the first one, I'm pretty certain that they were informed that more would come if they didn't resign. Now, of course, I believe the U.S. only had 2 bombs, so
We had
there's
3.
a limit
Three,
to what could be
three.
done anyway.
3.
They were going to come along sort of one every couple of weeks.
Right. The third one wasn't ready yet, but you're right. In about a week or so, it'd be there. You're right.
And
Charlie?
yes,
But what was the rate of production at that time? Namely, after the third one, how many more weeks would take for a fourth one, let's say?
I think I don't really know the answer to that, but I would speculate that since nothing was going wrong and all the things that had gone wrong in the production line had been more or less patched together, I would think they were going to have a bomb every couple of weeks.
I agree.
Charlie, can you hear me?
I do. I can.
I met both Frisch and Meitner as a younger scientist. And I can tell you briefly my impressions of them. I was a student at Cambridge University from 1953 to 55. Frisch was at Cambridge and he gave lectures in atomic physics. And all I can say is he was a charming lecturer, very clear, very European in the sense he was Dutch but spoke English quite fluently. So I enjoyed his lectures. I had no idea about him professionally. I was young and naive. I didn't know anything about the world. So I never had a chance to ask him about working with Meitner. Some years later, I encountered him again at an atomic physics meeting. Frisch had done some really important experiments in atomic physics. In fact, the first experiment to show that that molecules had a de Broglie wavelength. He showed he showed the wave nature of molecules, which had not been demonstrated at that point. I won't explain the experiment. It was a beautiful experiment. I asked him about the experiment after the conference. Everyone went down the Rhine on a Rhine boat. And if anyone who's done that on a nice summer afternoon with lots of wine aboard, you know, it's a very pleasant experience. That experiment was quite beautiful in that it showed a small anomaly in the data. The data was good, and it was really rather puzzling at the time. But later, it was explained theoretically by two English physicists. I told Frisch how much I admire that experiment, and particularly the beautiful theoretical explanation of this wonderful little detail that he observed. And what he said was, "Oh, has someone figured out the theory?" I think he was pulling my leg. I think he was just being humorous. But anyway, it was sort of typical of his rather gentle personality. In the 1960s, when I was at Harvard and working on an atomic clock device there, the hydrogen maser, under my supervisor was Norman Ramsey. And one day Norman brought a little old lady into the laboratory. She was rather short. She was very gregarious. And this was Lisa Meitner, who had just sort of one of visits. So my impression was very short, but it was a very strong impression. She was one of these effervescent people who just kind of lit up a room when she came in. You know, she was really interested and she asked questions. And my only impression was that this was really a wonderful person. So that was the extent of that. Of course, Norman himself played an important role at Los Alamos. He didn't like to talk about it, but I asked him, you know, about the experience, and he said that everyone was desperate to get the bomb built before the Germans got it. And that was so much taken for granted. There was no discussion about the use of the bomb or the, you know, the ethics of it. It was just to get the bomb dropped. And well, I think that's a well-known fact. But he was uncomfortable being involved with it. But he did point out that the effect of the bomb was to save lives. And he said it wasn't the American lives that were saved, it was the Japanese lives, because they were being destroyed at this high rate at that time anyway. So that was his way of dealing with this situation.
Thank you very much. Charlie, you did a wonderful job.